We're inventing a universal runtime model for all materials, whether they're created by artists, captured from measurements, or generated from text prompts, and to render them at all quality levels from consoles and VR to film rendering. Real-world materials feature incredible detail and visual intricacy like the translucency of plants, dirt on a well-worn pair of shoes, or the reflections on a glazed ceramic with dust and water spots. Realism depends heavily on how well we model these subtle but very important details. Offline rendering achieves a realistic look using sophisticated shading graphs, but these are too costly for real-time. Our main idea is to replace these expensive, specialized shading graphs with a universal and computationally efficient graph, a neural network, which enables 12 to 24 times faster shading calculations. Here are some comparisons between the reference material, defined using a shading graph in the bottom right, and our neural representation in the upper left. The model really captures the looks of these materials, matching not only the complex behavior of the reflections, but also the fine details on these intricate surfaces. At render time, using a neural material is a lot like using a traditional material. At each hit point, we look up the latent texture and evaluate two MLPs, one to get the BRDF value, and a second one to import and sample the outgoing direction. Some key technical innovations include built-in graphics priors that improve the inference quality, and a training time encoder that lets us support massive resolutions. For instance, these objects have textures up to 16K in resolution. In a game, this allows players to zoom in and to enjoy the kind of detail that previous neural models, here on the left, can't capture. Our neural model in the center here reproduces the detail and rich subtleties that make the reference materials so appealing. At the same time, it runs fast, and we can scale gracefully across different applications. For instance, using a smaller network on the left, we can render a full HD image in 3.3 milliseconds, whereas the slightly bigger model on the right still only takes 11 milliseconds and is visually indistinguishable from the reference. Thank you for listening.